So recording in progress. Let me put this on. Done. Silence. And let's make sure that I have the right. Wrong. Correct. This is a test. Fantastic. Sharing my screen. All right. I don't think there's anybody yet in the room. Okay. Shall I wait a minute or two, or do you want me to? Let's start. Julio. So, just to recap, this morning I said, and given that I will draw my diagrams from bottom to top for this last lecture, I'm going to rewrite causality as this. This is the statement that the process, some process P is causal. And this is in some process theory. So for example, in quantum theory, so for quantum systems, the discarded map on CD is defined to be the sum J equals 0, D minus 1 of the bra. So it's, but obviously this would be in the doubled category. So it's this would be the trace. It's a partial trace. In the case of a classical system, the discarding map would be defined to be also the sum of the effects, but in this case they are classical states. So here J can be any orthonormal basis, and here J equal 0 ... D minus 1. You just have one orthonormal basis for classical systems, so there's nothing particularly. So these are just the deterministic states, if you want. Or the points of the underlying set. So bunch of things. But causality is just about processes. You don't need quantum theory. It can be about many other theories, and you can ask, what does it buy me, really? And so we can consider a big diagram. In fact, we can start with a simple diagram where we have two parties that are space-like separated, or there's a diagram that's written like this. And so we have some processes, they have some inputs, they have some outputs. And I'm interested in whether what I do on the left can affect what happens on the right. And so I have three processes, A, B, and psi, because this will ultimately be, let's say, the Bell test or teleportation, or we'll see what it is, like different applications, but just to give an example. And I go in a setting where A, B, and the initial state, psi, are all causal. Or in the nomenclature of QIP, Shor boxes, or in the nomenclature of operational probabilistic theories, deterministic.
When you said a spatially separated in this context, it's just basically there's no
just
inputs.
For now, let's just that diagram there. There is no
Actual space.
There is no line from one to the other. So there is a certain partial order between the boxes, as long as you don't have loops. If you have loops, then things become more complicated. So for now, we consider diagrams forming a partial order. So no loops, no cycles. And then we'll talk about how you deal with cycles in some cases. And I already mentioned this morning that there's a very heavy price to pay for having time loops. So that's in itself problematic. But the point is, these are all causal. What does it mean that they're all causal? It means in practice that I can discard them, if you will. So another way to say causal is discardable. So if I write them and discard their outputs, all of their outputs, I get the discarding maps on their inputs. And in the case where there are no inputs, what I expect to get is the scalar one. So a theory that only has causal maps only has one scalar. There is only one thing that can happen. But of course, we are typically interested in looking at, let's say, post-selection, or in looking at the probability of outcomes. So we don't just want to restrict to one scalar, but if you want to be strictly talking about processes and nothing else, so you want to say a measurement is not about computing probabilities, it's just a process of measuring, and there is a classical outcome, then you can work in this setup where you don't have any other scalars. And so now we ask the question, what is the state according to the state as seen from Bob? So Bob, in Bob's past, let's say that these are two parties, and we look at the causal past and the causal cone around one of these parties, and we ask, what is the local state at a certain point? So we say, this is the slice at which I want to compute the local state. I want to see what it depends on. And so I go to its past. And I get something like that. So there is a notion of looking at the parts of the diagram that my wire or wires, we'll do a few more examples later on, depend on, and discarding everything else. And so what I want to do is I want to say, I want to define the local state in here and ask, what does it depend on? What is the local state? And because I have restricted myself to causal processes, all I have to do is discard A. I'll put them side by side so that it's clear. And if I discard A, because A was causal, I propagate the discarding downwards. And what I get is something like this. And in fact, I can push it lower, and I can just... And I discover, for example, that there is no connection between the input of A and the output of B. So the output of B does not depend on the input of A. This is no signaling. It's the equivalent of a no signaling scenario. So there is no connection. No signaling. They factor. And so I obtain that in this process, the input of A is discarded, and it's important that it ends in the discarding map. If it ended in some post-selection, it would be relevant because you would get different probabilities. But in this case, the input of A is discarded when you only look at the state of B, at the output of B. And so for the output of B, the only thing that it depends on is the input of B, but not the input of A. And this is the diagrammatic incarnation of the no signaling principle. And now you can look at teleportation. So quantum teleportation, the quantum teleportation protocol. And so we move to the ZX calculus. And we say, so let me take, again, my thick and thin, through thick and thin. How does teleportation work? So I take, there's some wire that comes in. The two parties share an entangled state. So at the start, They share an entangled state, and then they go far away. So at the start, they were together, but then at some point, they kind of, in fact, let's say that this comes later. So they start together, and then at some point they are separate, and they go far, far away, and there's no signaling allowed between them. And then Alice wants to send some quantum state to Bob, but obviously she can't just put it in a container. So what she does is she applies like C naught, and then she performs two measurements, one in the in the X basis, one in the Z basis. And on the other side, we want to know what Bob sees. So what is the effect of this? Sorry, this is the X basis measurement. So what is the effect of Alice plugging a state into whatever state she wants, obviously, into the left-hand side? Does the act of teleportation do something? Does it actually move things around? So from the point of view of Bob, does Bob know that Alice performed the measurements? Because that's the important question. Just locally, is the knowledge of Bob, is there information that is transmitted by the sheer act of teleporting something? The answer is going to be no, because that would be extremely problematic. So really the local state at Bob is something like this. So this is the state at Bob if Bob doesn't receive any information from Alice. So as far as Bob is concerned, this is the local state at Bob's without communications from Alice. And so we can apply our rules of causality to compute what that local state is and to check whether Alice's operations had any effect. And now the first thing we do is we observe that measurements are themselves causal. So that if we discard the outcome of a Z measurement or an X measurement, so this is the Z measurement, and this is the, sorry, that's the X measurement, this is the Z measurement. I think I have done this wrong. Yes, I have done it wrong, definitely. I put the wrong cross. That's correct. So if I discard the outcomes of the measurements, this classical outcomes, then that's the same as not having performed a measurement at all and having thrown away the system. So the interpretation here is not, again, a physical discarding. It's if I don't know the outcome of a measurement, it's the same as not knowing the system that got into the measurement. The measurement itself does not have any kickback. There's no effect from the act of measuring if I don't know the outcome. If I don't know the outcome, then it's the same as not knowing the income. So I can remove the two top dots, and I'm left with the C naught. And then again, I am discarding both ends of the C naught. And I will tell you now, but I will prove in a second, that if I discard the two ends of the C naught, then I also get, the C naught is also a causal map because it's a unitary or an isometry in general. And so I get that the discarding map propagates down. And what I'm left with is that the state at Bob's end does not depend on the input of Alice. So if I straighten this, I get that Alice's input is discarded and the state at Bob's end is the maximally mixed state. So there is a separation, remember, between these two. So this is Alice's side, this is Bob's side, this is discarding, and this is the maximally mixed state. And we'll get to how I know this in a second. So this is the effect of performing teleportation without Alice communicating any information to Bob. So if Alice doesn't communicate any information to Bob, then there is no effect. Bob sees the maximally mixed state. That's it. So let's look at a few examples of things that get discarded in quantum theory. So first things first, I'm going to claim that if I have a map that is just doubled and discarding it, and it is causal, so it's a pure map, U, which is causal. This is if and only if U is an isometry, i.e. if and only if U is inverted by U dagger. Only on one side, not on both. So I only care about one side. So it could have different number of legs at the top and at the bottom, and that's okay. So this could be I1, IN. This could be O1, OM, and N could be different from M. But that's my first claim, that the pure maps, so just the doubled maps without any additional traces that are causal, are exactly the isometries. And in particular, if they have the same dimension in the input and in the output, they are going to be the unitaries. So isometries more generally. And the proof of this is I'm going to take the doubled version. I'm going to say I start with the right hand side and I expand it. I'm claiming that I'm taking a map that satisfies this equation. And now I expand the left-hand side into its, like, I undouble it. So undouble. In fact, I should undouble it correctly. Left, right, left, right. Let me expand the right-hand side one first. I expand the right-hand side, I undouble it again, and double it. Also, I'll do the left-hand side after. And I get U star. And each discarding map corresponds to a cap. So I connect the outputs of one to the outputs of the other, like that. And I'm saying that this, on the left-hand side, I also undouble, and I get something like this. So this is I1 dot IN, and this is I1 dot IN, and this is IN dot I1. So I'm picking a convention by which I'm taking conjugates and I'm inverting the order of the wires so that things are kind of nice, but you can keep them in the same order, and then you just have some wires cross. This is quite common. It's just more aesthetically pleasing. There is no effect, because these wires don't really mean that there's particles in space. It's just the information about the wires. It's just tensor contraction. So the order is purely decorative purpose. And now I take this proof and I just open things up and I rotate the outputs into the inputs, and I get I1 IN here equals equals U dagger, which is what I wanted. So it's equivalent. It's just if you take the definition of what it means for a pure doubled quantum map to be causal, so in other parlance, a single a CP map with a single cross operator in it, and you ask which CP maps with one cross operator are causal, or which ones are CP-TP maps, it's exactly the ones where the cross operator is an isometry. So this is a known result for mixed quantum theory. So you can say the question here would be, in other words, this is CP maps which are CP-TP with one cross operator, and the other one says the cross operator is an isometry. And that's the equivalent statement in other language, maybe more familiar to you. So that's the statement, first statement. Second statement, it is true that the discarding map is just the sum from j equals 0 to d minus 1, the discarding map on CD, from j equals 0 to d minus 1 of the bra, the double bra for some computational basis. So sorry, some orthonormal basis. Phi j equals 0, d minus 1. And this is an ONB. So for every ONB, this is true. So you can pick any of them. You sum the basis states, the bras, the double bras for the basis states, and you get the discarding map. Why? Again, proof. So we start with the observation that there's a resolution of the identity in the orthonormal basis. So it's true that every orthonormal basis gives you a resolution of the identity as the sum of bras and cats in the basis. So it definitely, this is true. Or in words you may be more familiar with, the identity is sum over j of cat psi j, bra psi j. So this is what I've written above. And then I rotate, I bend things around. So bend one of the wires, bend the top of the wire in this case, and I get that this is the sum from j equals 0 to d minus 1 of psi j star. But then I can double or package, if you will. The left-hand side is the trace. The right-hand side is the sum of the doubled states, or in case the doubled effects. And that's my proof. So it is true that the trace can be expanded for a quantum system in terms of any orthonormal basis. So I can take the z basis or the x basis, I get the same result. And this is important because it allows me to prove the next part, which is that if I discard a measurement, a classical measurement, I get a quantum measurement. So next space. If I have a measurement in any basis, all right, gotta call it measurement in basis psi, where again psi j equals 0, d minus 1 is an ONB. And what is the measurement? Well, the measurement goes from CD to R plus D, because it goes from a quantum system to a classical system. And then this is going to be equal to the discarding map on the quantum system. So measurements are causal themselves. And the proof of this is, again, by undoubling. I start with the left-hand side. So I've measured in some basis. And I undouble it into its definition. And now here I have a bit of a, actually, you know what? I'm just going to do it in the Z and in the Z basis, because there is a bit of a problem with doing it in any basis. So let's start with the Z basis and then I'll discuss what the issue is. So this, I can rewrite the discarding map. That's just, actually, I didn't define the discarding map for a classical system. So let me do that first. For a classical system, you go. So I want the map that goes from classical system and throws away all of the classical states. So I want a map that has to satisfy the following property. If I plug in one of the classical states, which is just one of the Z basis states, because we took this particular convention, and I apply this map, I get single wire, I get 1 for every j equals 0 ... d minus 1. Unfortunately, I can't do the doubling thing. This is not a quantum state, or if you will, I don't have access to this double construction, but I don't need to do it for arbitrary states. I just need to do it for the computational basis states. And I have a map that works that way, because I can define my discarding map to be the discarding map for the computational basis. So remember, there was this spider states, and one of them kind of throws things away. This is technically underlying, it's the plus state, but it has the correct property. If I apply it to any of the computational basis states, I get 1. So for the classical systems, you just take the delete map for the basis, the least spider for the basis, and that acts as the discarding map. And so I can go here and prove that this is true. It in this case is in Z. Yeah, this is the Z basis. So that's the deletion for the Z basis is the plus state, because the plus state is the one that is defined to be plus inner product between plus and j is equal to 1 for every j. So that's the definition of the. So yeah, that's the thing. When in this calculus, you sort of have to identify the copy and the deletion for the classical states to be the ones in the basis that you pick to be your decoherent basis, if you will. That's why I try to avoid having to do the measurement in the X basis directly, because when you open up its states, they're technically plus and minus. So you want to think that I get 2 bits, 0 and 1, but more practically, you should label your bits as plus and minus, not 0 and 1, which has its advantages, because in some applications that's more interesting. But whatever. It's people call it the delete spider, but it's not the delete spider. You're right. It's not. It's post selection against plus technically. So, yes. So let's avoid the word. And it's the discarding map for the classical state. It acts as the discarding map for the classical state. And so now the proof is that if you have any, so this is any, this defines any special symmetric, so not necessarily commutative, Dagger-Frobenius algebra. So any basis, and I will actually say that this is more general than a basis, but maybe that's a comment I can make in a second. Then it is part of the definition of symmetry. In fact, it's just fusion. That this gives you a cap, and that the cap is going to, in fact, it gives you a cap which has, I should write it properly. You know what? I'm going to first write it for the Z basis, and then I'm going to tell you the rest of the horrible story that I have to tell you. So let's take the Z basis. Fusion, and this is the definition of the cap, is that this is the cap, and so I can repackage it as the discarding. And the reason that I want to avoid saying any other basis is that in general, the definition of the measurement is a bit more convoluted. So you have to keep track of which, you have to put a transpose on one of the wires. It's just that measurements technically shouldn't be defined like we write this for the Z basis, but the general definition for an arbitrary basis, say the Y basis, would be more something like the Y spider, copy, and a leg coming down. So there's a trace put in. So in fact, it would be defined to be the Y spider with a discarding map applied to one of the, it's a Y copy with a discarding map. And so this is, in general, not the same as writing this, right? Because in general, the cap for the Z basis need not be the same as the cap for the Y basis. So for arbitrary basis, you have to be a bit careful with how you define the measurements, but so this is a caveat. But let me go back to my non-complicated case of the Z basis for an arbitrary system, or the X basis in the case of a qubit is also going to work this way, but only for qubits. In fact, only for C2 to the n, R2 to the n. So for qubits, this is true. For Z2 to the n. So complex the algebra over, because the X basis depends on the group, right? So in that case, it's the legs are self-adjoint, sorry, self-transpose, and I can just do that. So that's fine. Now, going back to my causality arguments, after having proven a few interesting bits and pieces, I can look at a more general kind of processes. So I can ask, what if I have some process which has both a temporal component and a spatial component? So I have diagrams that are written over, let's say, a diamond lattice or something like that. Like an example would be the, let's say, X and T. So an example would be the processes that define on a diamond lattice, or on any other lattice really, the Dirac quantum cellular automaton or similar quantum cellular automata on the diamond lattice. So the idea here is that we're discretizing time and space in a lattice fashion. And we're saying that we take effectively a Minkowski spacetime. So this would be Minkowski. 1 + 1 Minkowski, to be precise. But you can do it in 1 + 2 + 1 and 3 + 1 with a different lattice. So this is 1 + 1 Minkowski. Flat, nice, familiar. And we take a sprinkling of a lattice, a discrete lattice in Minkowski spacetime, a regular one, one such that the causal order induced, the order induced on these events is the diamond lattice. So we want them to be effectively at 45 degrees left and right, exactly with the correct spacing, so that their causal order, the Haas diagram for the causal order is this. So I draw, and here we go back to the idea that there are some ways, various ways of putting diagrams onto spacetime. I take this, and this is the Haas diagram for the causal order. So the causal order is a partial order. It says event 1 is causally before, or it is connected by a light-like or time-like curve to event 2. And so it proceeds causally. And I just draw the Haas diagram because it's the convenient way to draw a partial order. It's finite set, so it works. And now on this, I want to put some process. I want to put a process, and I'll take the very simple. I want to put first some systems and then some process. The easy way to build something like the Dirac quantum cellular automaton is to say that that's a lot of points. Let's see if I can blow it up a little. I'm not going to try. No, that sounds bad. So the idea is you have how do you do something like the Dirac automaton? Well, you say each event has 2 modes added, and then it's a tensor product of the 2 copies of a Hilbert space, and one of them is the left moving mode, and one of them is the right moving mode, and then the evolution step happens in between the nodes. So I'm effectively working with the dual lattice in a sense. And I say I move to evolve it. You apply some unitary, a special one in the case of the Dirac QCA, but it doesn't really matter which. That takes the left moving mode and right moving mode from the neighbors at the previous step and sort of updates it. So makes them interact. And then you get two new systems. So this is one way to write this particular process. And now we do this for all the vertices, and it's the same. Luckily for a quantum cellular automaton, it's the same unitary. So the idea of quantum cellular automata is that they are invariant under space translation and time translation. So they're invariant under the translation symmetries of the lattice, because that makes them nice and easy to work with. And then I look at this. I repeat this process effectively many, many times. And what I get is a way of evolving the state from a set of points on some initial slice to another set of points. So I take a discretized view of what a slice is in space-time. And so I say, you would think of Cauchy slices, those are continuous objects, but you can have a discretized version where you just take a set of points that are not connected they're not causally connected. And so I can, for example, say that I take, let me finish drawing it. Now let's see if I can scale it up without breaking it. I think so. Okay, that worked. That worked remarkably well. Okay, so say that now you're interested in knowing. See, there are some dangling wires, there are some inputs, some outputs that don't go anywhere. And now say that you're interested in knowing the state, the local state at this event here. But let me just duplicate it. You want to know the local state at this event. You want to know what the state there is. And in order to know that, you have to look at its causal path. So you have to go down the lattice until you hit your initial slice. So for sake of simplicity, let's say all the way down, but I could have picked a different initial slice. And you take its path. Its past causal cone is something like this. Of course, I'm dramatizing it. Really, it is just a set of discrete points, because this is just discrete points. But I'm just drawing highlighting the entire thing. So on the right, I highlight the part of the diagram that I care about, and the rest of the diagram I somehow have to remove in order to compute the local state. I just want to have a function that from the inputs, I first want to identify what the initial slice is. So where do I have to specify my initial data? And then I want to have a single CPTP map that transforms my initial data onto the final data that I want to read. So I want to know what the state is at the end if I set any initial state. I want to know both where I have to set the initial data and what the final data is. And so I have to take this slice. I'm going to try to put as few of these as possible because I'll have to delete them later. And then I have to start discarding things outside of that cone. So I have to take all of the outputs that are not there, and I have to discard them. And I have to hope that my state is going to be well defined based on the past. And I know that it will be because all of these are unitaries, so they're all causal, but I still have to check what they are. So I start effectively consuming these unitaries from the top down. So I remove this event here, and I'm left with the discarding maps on its inputs. I remove this event here, and I'm left with the discarding maps on its inputs. And I say I remove this event here, done and done. So these were all independent. And now I look at the next layer, and I say, okay, so I have this one on the left. I've discarded both of its outputs, so I can remove it from my diagram. And I'm left with a discarding map on this dangling input, which will be irrelevant. And that. I can remove this one. And I can remove this one because both of its outputs were discarded. So I'm left with something like this. Again, some dangling input that will be irrelevant. So I know that that is not going to be part of my initial slice. And I continue doing exactly the same operation, discard the next one. I'm discarding one at a time just for, so that when you get the slides, you can, and I'm going to ignore the, actually, I shouldn't have deleted the discarding map. It's dangling, but who cares? And then I discard the last one. And I'm left with this. This is a description of what of the local state, its dependency on the past, and the inputs that I don't care about. And so I observe that this, wrong color, this, and this are irrelevant. So they don't, whatever state was there is kind of not connected to the rest. Not connected to the rest of my diagram, so I can disregard them. And then instead, so I'm going to ignore them. And at the bottom, I have identified what my initial slice is. So which systems I have to specify a state for. And it's going to be this. Let me take a very thick pen for it. So this is going to be my initial slice. So it's those systems. I specify a state for those. I know the state of the entire thing. And so I can remove my, I guess, all of this orange, which is annoying. And I can remove all of the green. And I can say, if I set a global state for the wires at the bottom, so whatever the initial state for the initial slice is, it can be entangled, it can be mixed, I don't care. This big CP map tells me what the final state on my desired event, so in H times H is. So that is the part of the diagram that contributed to producing the state at the end. And I do this by using causality again and again and again. I repeatedly remove things which were outside of the cone, and those are going to be my relevant parts of the diagram. And I restricted, and what I get is from a QCA, quantum cellular automaton, which is effectively just a giant unitary on space. Yes, I've represented it locally as a product, but if you take the entire lattice, you have a big unitary. And now by using causality, I say, if I'm only interested in the local state, starting from some slice, ending on some slice, I only need finitely many unitaries, but they're not unitaries because I need to discard their output. So what I get is a CPTP map instead. And this CPTP map encodes the process of field evolution. And in fact, this particular procedure is functorial. It respects parallel and sequential composition. So it's a functorial evolution of fields. It is.
I see that you are doing the temperature, but every time you do, you're increasing the temperature.
No, because deletion is not really deletion. It's just you do not have it's just a statement that your state here, local as you can observe it through your algebra of observables, is independent. You just don't have any influence from the rest. You're not erasing anything. No. This is not erasure. I think, yes, thank you. That is it's good to stress that. This is about knowledge, or if you want to be a bit more concrete about what can you observe. So say you have a, let me take a step back and then come back to this. Say you have a Bell state, right? Bell state, and you look at its marginals. So you start with a Bell state between two parties. And look at the marginals of the Bell state, the marginals for the two qubits. How do you write the marginals? Well, the marginal for the first qubit is obtained by discarding the second qubit, and the marginal for the second qubit is obtained by discarding the first qubit. And now we know that these marginals are the maximally mixed state. That is just the statement that if you only measure one of the qubits in the Bell state, and you take the outcomes from your X, Y, and Z observables on that qubit, tomography will give you something straight in the middle. And we can do it. So I'll do it now if you want. For everybody else. This is just diagrammatic. And in fact, this is perhaps a good moment to put a normalization factor in here just for the sake of it, so that we see that this is actually truly the maximally mixed state. So why is it the maximally mixed state? Well, we can compute the expectation values of various observables. So how do we compute the expectation values of observables? There is no way to write the expectation value of X in the doubled formalism because it's not a positive map, right?
Trying to understand the difference between solution and relation. So if I take a very state and I look only from the point of view of the new state of Alice, wherever it's at, what I get is that it's a trace, it's a partial trace of the other thing.
Yeah.
But I could think that if I do that, I mean, physically, that fixes some temperature. Okay, because I mean, physically, that's the way you do thermodynamics. And your chemicals, it's not about a state. This is what confuses me. It's not about a state of knowledge exactly.
Is it?
But it's a state about your disregarding, I mean, the environment, and that environment uses a particular temperature. Of course, that you don't have a particular, ensemble or anything like that. But essentially, you're doing a similar thing in thermodynamics.
Yeah, fine. So one way to let's see if I can hop onto that. So for example, would you say that when you realize if you have two quantum systems, they interact? So I start with my system, and there's an environment system, and I know that the environment is in some initial state, whatever it is. I make my system H interact with the environment, and then I take the environment and I throw it away. So let's say that my H is a photon, my environment is another photon, they interact, and then my photon remains here and the other one is sent out of in the expanding light sphere that will probably never come back to us, but it could in principle. So you never know. So would you say that the resulting CPTP map, so this is a unitary, of course, between my two systems. The initial state is pure, but this is in general. So let's say that U is a unitary and this is a pure state. But this is in general a CPTP map. So in terms of thermodynamics, quantum or classical that you want to have, this map would be considered dissipative. There is something dissipative about it. Would you say that this interaction somehow affected temperature in some sense?
This is called quantum dynamics.
But
quantization. So principle is not research. Okay, it's not very clear how it works. Okay, but in principle, it looks like there is a connection. It's not very clear what is the connection, but it seems that some people believing in EPH and all these kind of thermalization hypotheses, they would claim that you can define it.
Yeah. So in that sense, if you take temperature to be defined, even in the cases where all you've done really is take two photons, make them interact, and then one photon goes its own way, and all you're doing is saying, I don't have access to that photon anymore, and your temperature captures this idea that there has been some dissipative behavior because of loss of information, then yes, absolutely. The Bell state.
How you define temperature?
I am well, quantum. Yeah, exactly. How do you define a temperature that matches sort of the classical intuition? But even the classical one is problematic in itself.
That's a good point.
I kind of, yeah.
Exactly, but you see, there are problems because people have been trying to do that in real physical systems. And it looks like there is no well-defined temperature. Because depending on the observable that you measure, you get a different number.
Correct.
And the problem, this is the problem. The problem is that we do not know what is the origin of all this ensemble. We were indoctrinated. Okay, but we do not really know what is the origin of those ensembles, you know, the canonical, microcanonical, whatever. And it's an open question, it's not obvious what is temperature. It's one of the most difficult physical concepts.
However, what you can do, which you can do technically, is show that something like this, in fact, exactly these processes, the dissipative, so CPT maps, arise from a global unitary symmetry. So say a la Erlangen program, you take a big unitary system for the universe and you say, I have my giant, I have the universal wave function, whatever that means. I think the universe is a closed system with some unitary symmetry on it. And I say, yeah, I know, right? It's like, people call me crazy. You take that and you say, how do I in that see the local observers? How do I in that define what it means to have a tensor product? How do I in that recover that the local perspective is CPTV maps on quantum systems? And the answer is there is a way to do it. And perhaps later, if you want, I can show you what the construction is. But it is an open question how you interpret that. Is the ignorance actually, is it physical temperature? Is that there are notions of temperature that capture different aspects of it? Certainly, the idea that any of this is irreversible is not true, right? Because if you have a Bell state, you look at the marginals, whatever temperature is locally induced for the people, if you then go and put the two pieces back together, you can totally invert the Bell state and put it back into whatever initial state you want. So that the noise or the mixedness of taking marginals with this partial trace is always a relative concept.
Is something called Osmond echo. Essentially, you convert and go back.
Yeah.
Without essentially, being reversed. That's the whole point of thermodynamics.
Because in thermodynamics, the main assumption is indeed that you have, it's the heat path that is the.
I mean, we were indoctrinated.
Yeah, no.
We were told there are only microcanonical, canonical,
Correct.
canonical ensemble. That's what exists in nature. We can calculate temperatures, we can calculate everything. Great. We can, even the guys like Carnot, we didn't need this concept.
No.
Okay. But the reality is when you are trying to use fundamental physics to explain that thing, it's one of the hardest concepts. You cannot explain the second law of thermodynamics.
It's, in fact,
It's the hardest problem we have.
I wouldn't go so far as to say, with some motivation to back, if anybody wants it, that the second law of thermodynamics is, it is often taught as a fundamental cardinal rule of the universe. Some people try to make theories and extensions of quantum theory based on generalizations of the second law of thermodynamics. And the reality is that in practice, the second law doesn't apply to almost anything. There is no such thing. Well, there are such things as open systems, but there is no such thing as an infinite heat bath. And the closest thing we have to an infinite heat bath would be space out there, except space is full of gas. Gas collapses under its own gravitational influence. And it so happens that it has negative heat capacity. So when it collapses, it heats up, which is weird because it's lowering its energy and heating up. So it's not a heat bath in any sense. Empty vacuum would be, but there is no such thing as empty vacuum around us. So there is, the second law has very limited applicability. I think it's problematic. I always found extremely.
One of the hardest problems is.
Yeah.
Penrose, you have Penrose nearby. Okay, so then books
yes, indeed. Well, then I also have Deutsch nearby, who says that probabilities have to be eradicated from the foundations of physics. So, great influences bouncing around me.
Do you think the tracing itself actually changes the information content? I mean, in some sense that, the entanglement
So tracing as in the fact that you're considering the marginalized state, of course, changes. It loses information always. It is a dissipative process. And in fact, let's take that as the segue for purity. There is a thing called the purification principle that makes that idea precise. When it says this quantum theory satisfies the purification principle, and other theories don't necessarily satisfy it. So it's not enough, unlike causality, which pretty much every reasonable theory of physics should satisfy, because otherwise it's not compatible with general relativity. And then we could argue that maybe that's what we want, but still, what is time if we can receive information from the future? I have no idea. But maybe we can, I don't know. But the purification principle is a bit more sensible. It's practically useful. It allows you to draw some very nice conclusions. And it states that if I have a map that's pure and another map that's pure, and I have an equation like this. So if I have effectively a map that's obtained by discarding some environment, okay, so it goes from A to B, and there's some environment that's discarded, and on the other side I only have A and B, and the thing on the left is pure, so it's doubled. G is pure, i.e. it is equal to just a double map, G star, A, B, B star, technically. Okay, so we start by saying, what if can we discard some environment and obtain something which is again pure, which is again unitary or isometric? Can we do that? And the answer is, well, yes, of course you can, but under some conditions. And the condition is that the environment must be completely disconnected from the rest of the map. So this implies that the process that you discarded was actually disconnected. It was G times something in the environment that had nothing to do with G. Not only, that's one part, and then you could ask this is any pure state of the environment. So the environment was in some state, it has to be a pure state because the map on the left is pure. And now I do you one better, and I say that there's a essentially unique purification principle. So it's called the EUP, essentially unique purification principle. And it says that not only is the purification principle true, but actually you have very few choices for what you can discard. If two pure maps are equal when I discard some bit of it, and they have otherwise the same signature. So if I discard the same environment or the same system in F and F prime, then I get an equation like this. Same input, same outputs, doesn't matter, and same discarded system. Then actually, this is EUP, it's called. Actually, the two maps originally must have been very similar. There is some unitary. There is some unitary from E to E, which makes this true. And I can make it even more general and say that I don't even need a unitary, and I don't even need the environment that I discarded to match. I can take a different environment And then there is some isometry. Which makes them equal. So there is very little that you can do in terms of discarding. If you discard two pure maps, and you get, first of all, if you discard a pure map and you get a pure map, that means that the map that you had originally, the environment was disconnected. And if you have to, that says entanglement always creates noise if you discard one part. The marginals of entangled states are never pure. That is the only states whose marginals are pure are product states. So we can prove that. So with the purification principle, we can prove that if I have a state such that both marginals are pure, so I discard one or I discard the other system, and I get some, I probably should have used a thinner pen for the labels. One sec. There you go. So I get, if I have a big psi and I discard it, and I get phi1, phi2, pure states. So bipartite AB, I discard B, I get a pure state on A, I discard A, I get a pure state on B. Then my state, my original state, must be a product state. In fact, I also know what the product state is because I know its marginals. So this is an important result in quantum information, that if I have any bipartite state whose marginals are pure, is a product state of its marginals. And you can prove this with those two principles. It's very straightforward diagrammatically. So the proof is, in fact, let me just rearrange my thing a little so I can fit my proof, because it's not long, but it's also a bit longer than one line, I think. So like that, I can move this up. Yeah, kind of. Hang on. I'll manage. Okay, so the proof of this is straightforward with the purification principle. It says, because I have the left marginal that is pure, I'm going to fill it in a sec, then the original state must be a product of two things. And then I take to identify what the thing on the right is, I'm going to discard the other side and obtain my result. So hang on, let me fill things in. So if I take big psi, discard the system B, and I obtain phi1, then by purification, this belongs before essentially purification, I get that my original state on A and B, so the bipartite state, is a product state, and the left is certainly phi1. Then I discard the right, and I obtain that. So this is going to be called star. This is star. So I get that my original, my phi2 state, is just a marginal on B of my big psi state. But I now know that my big psi state is a product state, so I can remove the marginal on A. I can discard it from the equation, and I am left with just my unknown bit on B is actually necessarily phi2. So this is the end of the proof. That's quite a nice, neat application. It's an important result that you can prove with just this diagrammatic axiom. It's just about disconnecting things and sort of splitting. And another, the essentially unique purification can instead be used to prove that if I have a bipartite state, such that, so I have some bipartite state, and then we'll get to Gerardo's question from yesterday. What are the states that have what did you say it was called? The purification, purity with respect to some algebras. Well, with respect to the SU, in this case, yeah. So we'll start with the bipartite case, and then we'll do the tripartite case. So in the bipartite case, if I have a pure bipartite state, such that, so this is on AA, so on the same system twice, such that the marginal of this state is the maximally mixed state on either side, it doesn't really matter which, then my claim is that necessarily my original state must be the Bell state up to a local unitary. And again, this for some U unitary. So that's going to be my claim. And the proof of this proceeds as follows. If I start by saying this is my equation. My marginal is the maximally mixed state, i.e. it has purity 0, because purity 0 is the same as saying that it is the maximally mixed state. But we'll get to that in a second. Then I can twist the maximally mixed state to a shape where it looks like a discarding of some bipartite state. Which bipartite state? The Bell state. So I can just twist it and do that. And now I can apply essentially unique purification, noting that the environments are the same, to conclude that necessarily there exists a immediate. I conclude my result from an EUP. It's directly essentially unique purification. It says that actually that if they are equal when you marginalize, they're both pure, they're equal when you marginalize them to the left, then they must be equal up to a unitary applied to the system that you discarded. And that's the end of it. That's the end of the story. So it proves that any state which has one maximally mixed marginal has to be the Bell state up to a unitary, which is an interesting result. And now we can get something about the question that was posed yesterday, which is, if I have a state, and that question doesn't have a full answer yet, I'm afraid. I tried to complete the proof, but I only got quite a bit far into the proof, but not entirely. So we can maybe pick it up. And the condition is that the three marginals of this, the three local marginals, so marginalizing this state to the individual subsystems gives you the maximally mixed state in all cases. Then we would like to conclude, but I don't think that's entirely, I don't know if it's true entirely, but I'd like to think that it's a good conjecture, but I didn't get to the point where I can fully prove it. It's definitely not a GHZ state, as in not just a pure GHZ state, but that doesn't matter. It could be a GHZ. I would like to conjecture that this implies that it's the GHZ state up to some local unitaries, so that this is any GHZ state up to some local unitaries. I don't know, maybe this result is known, but you say that, I mean, I don't know about it. And
we know in a different way. Yeah, but you see,
you know that this is true, that this holds?
I mean, what I know is, or at least what we prove, is that if you have the GHC in one direction, then that is true.
Oh, the other way is certainly true.
Yeah. Okay.
This is true. This we can prove easily. The other.
Then it's not repeat. I mean, the only state that has minimal purity is always the GHC state, at least in the
Up to local transformations. In any dimension?
What do you mean by that? Oh,
That's, I don't know. I am completely like.
yeah,
So on the
I
left,
need to think if it was done in.
so the left is easy to prove in the sense that going right to left, all you have to do is prove. I mean, the GHZ state is symmetric, so I'll only need to prove one case, and it's pretty straightforward to show that. I mean, I guess this is a problem of practical interest. So let's start with the discarding the first and the second, and then the other ones are effectively analogous. So you take this, and what you get here is the final part is the interesting part, I think. So for now, this is easy because you're just discarding two unitaries, so unitaries are causal. The part that's not entirely easy is to understand that that results in a maximum state being passed under V, and that you propagate it. So that's not straightforward, but it is almost straightforward. So what you do is you deform this state diagrammatically, and you obtain two discardings, copy map, which is an isometry, the transpose of V, which is a unitary, and then the copy. So this will be V transpose, and you use the fact that if V is unitary, V transpose is unitary. And this you can prove again diagrammatically. It's not hard. But now that you have things in this form, you can push down because so this is because U and V, that was W actually, sorry. W, U and V are unitaries. So they're causal in particular. Here you use this fact, here you use the fact that the copy map is an isometry. So it's causal to push down again. And then you will ultimately use the fact that VWT is unitary to get this, which is just a maximum link state. So you use the fact that WT is unitary. And that's the proof in one direction. So the proof in one direction is straightforward. It's easy. It just relies on you being able to take the GHZ state and realize that actually you can shift it into a copy on one side and a Bell state. So it's a Bell state plus a copy. So that's easy. The other side requires purification. In fact, requires essentially new purification. And you start by observing that, so this is the proof of the other side. You start by observing that if you marginalize and you obtain the maximum limit state, the maximum limit state is the discarding, we've just done this trick, of the copy map and the Bell state. And so by essentially unique purification, it must be the case that your original state, in fact, I can use that your original state should be something like this up to a unitary of some kind. So it is a GHZ state, but where one of the sides is unitary. And I'm going to just make it a bit easier, and I'm going to conjecture, since I know that something like this is an isometry, I'm just going to now write that I am interested in states which satisfy the following, which are in the form in this form, because that's equivalent, F for F iso. And now the cool part is that you can conclude something about this F, is that F is an isometry. That doesn't tell you much, because it could be any isometry, right? It doesn't have to be related to GHZ. What is one of the interesting properties of GHZ states is that if you take, e.g., you could take F to be the copy map with some, okay, let's take the copy map. And then there are some interesting consequences to this fact. An interesting consequence to this fact is that F transpose with one leg up is an isometry, because it is again and that F transpose with the other leg up is also an isometry. And you can change this by putting U, V, and W here, and WT, I guess. And then when you transpose things, you get, so let me just make sure that I do it right. You get W here, the bottom left is UT, and this is V. And you get, for this one, you get, let me give a bit of space. You get W here, you get U, and you get VT. And these are all isometries. That's the nice part about the GHZ state. And in fact, with purity, you can prove, with purification, essentially unique purification, you can say, I now have, no, I don't want to duplicate it, sorry. New slide. I now have this state, which satisfies two equations. If I marginalize it on the right, I get the maximally mixed state. And if I marginalize it on the left and sort of bent leg, I also get the maximally mixed state. So I get these equations. And now with essentially unique purification, I indeed get from 1 and 2, I get from 1 that indeed the left bent version is an isometry, and 2 that the right bent version is an isometry. So while I can't prove that this is in the form of a spider with some unitaries, I can definitely prove that it behaves like one. And this is just a consequence of purification. So I now have a map such that all three ways of rotating it with legs up and legs down give you isometries. And I know that's not the GHZ state up to local transformation, but it is quite close to the GHZ state up to local transformation. There's probably a little bit more, I mean, there's definitely a little bit more work to prove that this is the only case, but at least you get the correct compositional behavior. You get that if you take this map and you rotate it in any way, you always get isometries. I mean, I'm pretty sure you can probably look at the diagonal of this and conclude that that's the GHZ state. You can get some more. I mean, I got some more progress, but I sort of, it's more of a observe. What if I take a computational basis on the input and I look at what the outputs are? They're entangled states that satisfy 3 properties. It's fairly easy to build these maps. I don't know whether they are just the GHZ states. I think so, but I'll try. I'll work on it.
Yeah,
but you say.
Yeah, yeah, but it's interesting. I mean, I don't read it this way, okay? But if you want to determine, you know, not for 3 parties for 2 parties, simple like 4 or more parties.
And then ones with purity 0.
For all possible parties.
One.
A and E, absolutely maximum.
So any discarding of any number of parties.
Any numbers of ways that you were dealing with here, there is no more than those partitions. But it's like
No, that's
5. No, I mean discarding 2 at a time. I mean, what you are doing is
you don't mean leaving only 1 at a time. You mean
saying is if I give you 4 qubits.
Yeah, correct. And I have a state on 4 qubits. Let's start with that.
4 qubits. Now you can look at all possible partitions of 4 qubits.
Yeah, but I don't know what that means in terms of all partitions between discarded and non-discarded.
You have 1, 2, 3, 4.
Yeah.
You can partition 1 with 2, 3, and 4. 1 with 3, and 2 and 4.
So partition in 2 groups of 2 and 2.
Well, in this case, well, in any number, but you see, if you 3 and 1 is not, because 1 is not done. So it's only with 2.
So you want states
partitions.
Okay. So you want to take okay, and what is the requirement? So you want to say that, let's say these 2, what is maximum?
So, you know, the requirement is that you partition
Yeah.
1, 2, 3, and 4. Put in a square. And let's not use this notation. Put in a square.
Okay.
Put in a square. Put in a square. Each vertex of a square is 1 cubic. Okay. So make like dimers notation 1 and 2, 3 and 4. Like dimers. You know dimers were
No, but
dimers. It's like a oval. An oval going through
like this.
Yeah.
Okay.
One,
Yeah.
2, this is 3 and 4.
Yeah, sorry. I rewrote it incorrectly. Yes. So let me just,
For example, 1 and 2 and 3 and 4.
yeah. Let me make copies of this. How many are there? Quite a few, right? So let me just make a small ones.
Only 3 ways of partition. 1, 2, 3, 4, 1, 3, 2, 4, 1.
Of a square, you're right.
3.
Okay. Only, but in pairs you want.
Pairs. Well, in this case, it's only in pairs. If you have 5, there are also.
Okay. Yeah, no, I'm following. Yes.
These are called A and B states. Absolutely maximum.
But I don't know what the requirement is. Once you partition, sure, I partition.
Yes. Then, for example, that's one partition. That's another partition and diagonal. Exactly.
Actually, let me do it in.
So the states that you're getting when you do that should all be maximally entangled. So every time our old possible way is a very interesting problem.
Hang on. Okay, I got it. I think I got it. Maybe I didn't get it, but I'm trying.
So indeed, you can prove that for 4 qubits it doesn't exist.
What do you mean?
Well, what it means is that it's not absolutely maximally entangled.
So you want to prove that this.
There is no state. You have to find a state of 4 qubits such that under all partitions, if you trace out one of them, the others are always maximally. So there is a proof that shows that for 4 2, so what is called AME 4 2 doesn't exist. AME 4 4 exists, but you need to be smart how to do it.
So this, where I discard left 1, what did I say, 1 3, or I discard 3 4, I discard 1 4, or 2 3 in the middle. Okay, got it. So that I get, and so you say this has to, yeah, all right. This is, yeah, this is, it's very easy. This is very easy to prove.
What I'm saying is that what is not obvious in general, if I give you AME and N, I give you any number of parties in any dimension, how to make a periodic table of existence and non-existence of these.
Interesting.
And these states are important for communication.
I mean, this is the proof that that no such states exist. I mean, no, as in, I only need 2 of them, right? I need to use this one. So I'm gonna take star and dagger. So I need 2 of them. I take these 2. I'm just saying, I mean, purification is an incredibly powerful tool. It does things that, it makes things easy. So if I use, so I take only those marginals. So I say the marginalizing a 1 2 must give you maximally entangled state. So bell state with some unitary. And marginalizing 2 and 3 must also give me a maximally. And I pick those 2 because they have overlap in the systems discarded. And now I say for the statement from star is this. That's the same as discarding some bipartite state. I don't really care what. And by essentially by purification, I get that the 4 qubit state must necessarily be a tensor product of the maximally entangled state and some bipartite state of some kind. And then I take 3, and I want to satisfy the other equation. So dagger, so I marginalize the middle 2. That discards 1/2 of this bipartite state. I don't care what it is. Discards 1/2 of the Bell state. That gives me some local state, which is probably mixed, but I don't care. But on the second qubit, it gives me the maximum mixed state. So this is certainly not the Bell state. And this is kind of the end of the story. So you even 2 of these equations you can't satisfy. You don't need all of them.
But I'm saying that the general problem is solved.
For arbitrary partitions.
For, this is called the problem is AME, absolutely not in time.
Yeah.
Parentheses. N, number of parties.
Yeah. AME,
parentheses,
N,
comma, M.
Okay, so this is the number of parties.
The other is the dimension of the equilibrium state.
And what kind of partitions do you consider?
No, they must be all partitions.
No, but of course they can't be partitions where you're only left with one state.
No, that you don't consider. I mean, all the ones, for example, if you have 5, you can do, just
3, 2, 2, 3.
Yeah. Because
Because you always want partitions into 2.
But you need at least
Correct.
some partition that has to.
And then it's okay. How dimension?
In particular, there's a physical regulators of 1 year ago. That is that because all these problems have to do with so-called combinatorial. Quantum combinatorial. It's called now quantum combinatorial. And the things are connected to quantum sudokus and Latin squares and Latin squares. Yes, quantum sudoku. So there is a paper.
Yeah, Latin squares are pretty neat. There's some applications of the ZX calculus to them by Vicari and others. But sorry, I didn't mean to interrupt you.
That there are some that are very difficult because, for example, some of the states we can construct using graph state or generalized idea of graph state. Not just the usual graph state, but a generalized idea of graph state. But there are others that is not obvious. And in particular, this one that is the one that appears in the physical regulator, that is AME 6. 4, 6, 4 parties, 6 dimension 6. So they prove it exists, but the numbers you need is the golden ratio. How the heck the golden ratio appears, nobody knows.
Okay, but these states have to be okay. Interesting.
I'm just telling you, it's an open problem.
This is interesting. So for pure states, there's definitely none in dimension 4, right?
No, I'm saying all these are pure states.
Yeah.
From the very beginning.
Yeah.
Okay? But some exist, depends on N and M, some exist, some do not exist. Okay, but in particular, there are some of them that they exist. And the state has faces and numbers that do not coincide with the dimensionality.
That's interesting. So they have to be. That's fascinating.
The origin of the golden ratio. I mean, golden ratio you can get whenever you have faces that are e to the I pi over 20 or pi over 10.
Well, it's fascinating.
If you have 4 C's, there is no way you get pi over 20 or pi over 10. So where are these numbers coming?
So you want maximally entangled with respect to not G, doesn't mean GSZ, right? In this case anymore. It means maximally entangled with respect to, not with respect to the same, to this metric here, right? Not with respect to this idea of marginalization, because in that case.
No, it's not this thing.
The maximally entangled, for example, that also includes the W state and the GSZ state for the tripartite qubit case.
No.
No.
No, I'm saying for tripartite, if you are having, let's say,
5 parties for qubits, so 5, 2.
Phi2 is not that is 0, 0, 0, 0 plus 1, 1, 1, 1, 1, 1. It's not that one.
So for phi, yeah, no, I'm saying when you say maximally entangled state, let's say for 3 qubits, you would not just restrict to GHZ states up to local transformations. It's more than that.
Yes, but I mean, 3 parties, 3, that is like what you're doing. 3, 2, it is yes. It coincides. 3, 2 coincides.
Does
As
it?
I say, for 2, 2, it coincides, is better.
For 2, 2, it's concise. Yes, for 3, 2, but for 3, 2, it is GHZ. Yes.
Yes, it is.
Because
But then when you go to 4, 4, 2 doesn't exist.
no, sorry, I'm that's fine. I'm asking the thing that it has to be equal to. So you say this has to be maximally, the marginals have to be maximally entangled.
4 partitions.
Yes, of course. But when you say maximally entangled, you mean maximally entangled in the usual sense of the notion.
Yeah,
So for example, for 3 qubits,
maximally entangled means that
it
if
could
you
be,
trace out everything, you will get a maximally random state or whatever.
oh, there's other definitions of that actually.
No, well.
Because in the W state, if you trace out everything, you don't get the,
Right, but that's not maximally entangled in this sense.
in the sense, that's what I wanted. So if it's the, okay, I get it. So something where you trace away and fascinating, absolutely fascinating. Thank you.
It is a very open problem.
Very nice. See, I learn new things. But yeah, so in a sense, some proofs of this kind you can do by using purification and not even looking at the inside of the state, because purification is a very broadly applicable technique. So all of these, a lot of results from quantum information ultimately boil down to some application of purification or essentially unique purification. And diagrammatically, you sort of hide away a lot of the complexity. Like you don't have to look at entropies. You don't have to look at so the expression that you gave me yesterday, requiring summing the squares of the oh gosh, yes. So sum over mu equal x, y, z, but actually mu in the generators of the algebra, summing over the parties of what? In this case, it would be it's the trace of mu j rho squared. Yeah, so this, and for example, asking that this thing here is 0 because these are all squared is the same as asking that if you take your state and you marginalize, you take your rho, whatever it is, and you marginalize all parties but one, for all parties, you always get the maximally mixed state. So if you leave the first one, so that's a diagrammatic equivalent of, that's what I used to.
The absolute maximum integration.
Yes.
Where all partitions.
Exactly. So this is the case where you pick the partition. In fact, this is the case that you don't consider in the AME situation because it's the one where you only look at the individual marginals. Correct.
The AME is more restricted.
Yes. But this diagrammatically is captured by asking that the sum is the maximum mixed state. So that the marginals are maximum mixed, which helps work to me used to purity and essentially purification and diagrammatic notation. It helps me to reason by saying, okay, I have this diagrammatic equation, I can twist it and simplify and deduce things. All right, that's, what time is it? It's 3:35. Shall I mean, are there questions on this, or shall I say something about indefinite causal order and diagrams in there? What would you like? I don't mind. This is your time after all, not, I mean, I'm getting a lot out of this, but if you have questions, this is as good a time as any. Shoot. It's so the current interpretation of the field tends to be something like device independent tests or self tests of quantum gravity. So you are in a situation where you say, I have developed an experiment that proves quantum gravity. And one looks at the experiment and says, no. or yes, Nobel Prize. But how do you certify that? How much do you trust the intuition of the person describing the experiment, and how much can you actually verify? So the question is, can I develop an approach where all I have to enforce is the causal order between the events in the experiment? So I have to make sure that you truly did your operations outside of each other's causal cones. It's the usual timing. It's the same as the loophole in Bell tests. You have to sort of check the very last little timing, the very last bit, until you can prove that there was no way whatsoever for influence to travel left or right, because you want to presume that people cheat, not necessarily intentionally. And then you give me that, and you give me the numbers that come out of your experiment. You just repeat it with the various settings, and you produce numbers for me. And I put it in a machine, and I tell you with a lot of confidence, like I'm effectively certain that what you've witnessed is superposition of spacetimes, because there's no other way to explain it. There's no classical way to explain the ordering of the events. And this is sort of the indefinite, sort of device-independent, theory-independent testing of quantum gravity on an operational level. So where all you can rely on is the local experiment data, and you're not trying to infer that what you observe is spacetime from some more complicated models. Of course, you could make a model and say, I have this new model of physics, which I believe, I interpret, I describe to be a superposed spacetime. But then someone has to certify that what you said is sensible. And that's non-trivial, especially in a field as controversial as this. It's not that you will go there and say, I have this new model of physics, and everybody will be like, cool, I'm going to, yes, we'll take it. Most of the reactions will be, nah. And so you have to sort of be able to prove it somehow. And that proof is, if you can do it device independent and theory independent, because again, if you're doing new physics, you don't know that it's quantum mechanics. You don't know that the new thing that completely breaks the previous rules fits some rules that are convenient to prove that it works, but just not the others. So you have to be able to say, okay, without knowing what the theory is, only rely on sort of causality, relativity, stuff that I believe to be broadly true, or at least stuff that I have control over, because I can, on a large scale, I can say that one party was there and one party was there, and there was no business in between. I could see like clear sky. There was no superposition. But maybe locally someone managed to put two masses in superposition. It's just, I had control over the large scale part. I just didn't have control over that little exotic bit. And you want to only rely on that, which you know to be classical. Only rely on that, you want to say what we saw is quantum gravity. And so you can go and collect your big chunky medal. But yes, that's the main goal of the field. And then what people actually do is lots of different mathematically interesting things. Yeah.
It doesn't run.
It vanishes if you take it under up to Lorentz invariance. It does vanish. It doesn't vanish naively, but it vanishes.
But that is absolutely.
Yes, but because okay, if I see, go on. So if you look at the commutators that don't vanish, and you do calculations with the commutator that doesn't vanish, and you don't correct it in any way, and you get amplitudes and therefore probabilities out of that, then you get signaling. Because the fact that the commutator doesn't vanish outside of the light cone, if you don't correct for that artifact, you will get signaling, which is a problem. The thing is that the observables that you define are defined in such a way that you always do a Lorentz invariant measurement. Well, not true. In some cases, some changes. I mean, some people might argue that that's not the case, but approximately, it's true. Let's say. And so from the outside, the box that does the measurement, the experimenter's perspective, that commutator doesn't signal. You can't macroscopically signal in any way. You cannot microscopically signal either. You cannot observe it. There is no, it's not real. Then someone could say there are ways of making virtual particles real, and I don't know. I mean, that's not. I don't even know if it's well-defined problem. But it is as far as we know, and this is what the boxes capture. The operations that we know we can do on space-time don't admit signaling. Now, maybe it is that there is some form of localized small-scale signaling that does break relativity on a small scale, but not on a large scale. And the issue that I have with that particular perspective, if you want to take a purely naturalist perspective of the world, is that everything is in quantum field theory, we are fields, we are made of fields, everything is the same stuff. And so if you have something small that can be used to signal on a small scale, then it is perfectly believable that you'll be able to take that and make it bigger and bigger and bigger, and then you'll be able to build a signaling machine. And so that becomes interesting. The question is, of course, what energy would you need to do something like that? How likely is it that you can observe the signaling? For example, and this is a point that I have to remind myself of once in a while, if you look at just the probability distributions and you ask, are these causal? The answer for any experiment will be kind of, because just a statistical error on the data that you collect creates a little bit of margin where you can escape the polytope of causal distributions. You can be a bit outside of the slice because causality is an equation, is a set of equations. It's a closed set. So any small perturbation on your data gets you out of it. So you can never ask causal yes, causal no. You have to say causal most likely, almost certainly. And statistical noise in itself is enough to make it fuzzy. And so maybe it is that the statistical noise inherent in performing any kind of measurement at a certain energy level is always going to be so much that it hides any microscopic violation of causality, because it could be that the energy scale of that is always smaller than the one that you can use to probe it, in which case you never see it, right? It is there ideally, but if you are an empiricist, you're going to say, is it really? My view of the world, even in the limit, wouldn't be able to see it. Therefore, my maps are not. That's not there. But yes, from the perspective of the calculation, it could in principle be there, except we have these tricks where we cancel it out. We take the commutator and. But again, that is what we believe physics to be. There is no reality to quantum field theory. Quantum field theory is our model of what we have observed. It's convenient because it reproduces the results of very many calculations. It is beautifully accurate, but it is, let's remember, beautifully accurate in a setup where we have twisted it and decided that some stuff that diverges mathematically, we may converge by truncating with no justification. Well, actually now with justification, but at the start, just with intuition. And it works, and it's great. If it works, it's correct in a sense. As long as it works, it is correct. But it's still a model. So at some point, we might want to change our model and make models that are based on just observations, glued together. That would be my dream, but it's very hard. Like I see reality as the consistent gluing of the observation that we can make. And you can talk about diagrams that way. You can say, imagine that you could put transformations at all points of space-time optionally. And you can study all the possible probability distributions that observers would see by cutting out themselves from the equation, because some free will is necessary. And now take that, glue it together, because they coincide on most of the outputs. Causality makes it so. Glue it together, that's physics for me. Ideally, that's the monstrous object that to me ultimately gets collated into a physical theory. And I have a toy model of that, which I find, I know this sounds crazy, but there is a toy model that makes it not crazy. If you look at qubits, you can say, my model of a qubit is the Bloch sphere, or my model of a qubit with noise is the Bloch ball. And you can say that is my model mathematically. Or you can say, hang on, what can I observe? And you say, I can observe, I have a qubit, I can make all of these observations. And then you look at the observations and you figure out that actually, if you make 3 of those observations, that's enough to predict the outcomes of all the other ones. It's tomographic. You can do X, Y, and Z. They are in some sense independent of each other. And if you have them, you can take linear combinations and get all of the other ones. So you can describe all of the observations you can make on one qubit as linear combinations of these three, well, affine combinations of these three actually, and nothing else. And so you say, actually, the reason I get the block ball is not that I imagine I knew, I took classical electrodynamics, I got complex numbers, then I got Hilbert spaces, then I got pure states, and I asked, what is a mixed state? I got density matrices, I asked, what's a structure density matrix, and I got the block ball. But instead you say, I did some experiments, I saw that 3 of them are always enough, and I describe my states by the outcomes of those 3 experiments. I call those experiments X, Y, and Z. I plot them in 3-dimensional space with X, Y, and Z as the axis, and I get some points. And then I observe that these things are always in some bounded region. I never get more than one, or I only have 2 outcomes, so they stay in a cube, but actually there is some kind of uncertainty principle that makes them not a cube. So they're not independent of each other. They are related by the fact that there is a spherical surface that limits the maximum of accuracy I can get in either direction. So if I get too close to being 1 or -1 in one of the directions, I get close to 0 in the other 2. And that's just a spherical shape. That's because if you had a cube, you could get arbitrarily precise in all directions. But if you have a sphere, you can't. That's it. It's observations, and the geometry comes from the observations. The number of coordinates come from the observations. And I would say most of physics should actually ultimately be described like this, because our mathematical models come from that. They come from the fact that we tinker with things. We take neutrons and shoot them through some hoops, and we discover that apparently there is such a thing as neutron optics, which I didn't know until yesterday, but now I know. And we make a model for it. But ideally, as an experimentalist, you would say that those models are secretly a very complicated mathematical object that takes all of the possible observations we can make, and glue them together, and compresses them in such a way that we can talk about them easily. And that's no different than the Pauli basis tomography for qubits. You think, what is the space of all qubits, of states for like a 10-qubit system? And it looks really complicated, but actually it's just the tomography that comes from the Pauli strings. That's it, because it's a locally tomographic theory. And so, again, just is purely philosophical. There is no, some of it is, in some simple cases, you can make it mathematical. In other cases, it's too hard, but that would be my own perspective. I like to believe that what we describe comes from what we experience. And then someone tells me that I'm made of like quantum fields, and in a super deterministic universe, I have no free will, and that solves all of the problems on the locality, and that's okay by me. But I still like to believe that when I talk about things, I talk about actions that I can or cannot make. And to me, that's important. That's my perspective on the universe. But yeah. Other questions?
Back to certification.
Hmm.
I think that something that eventually, although started, in communication, quantum communication, I mean, it's a concept that should be spread across physics, because in particular, people working at the frontiers of this.
Yeah.
Okay, because it's a kind of, how can I say, logically constrained way of thinking about processes, right?
Yeah.
And you were asking the question before, but think in this way. 4 years ago, I think years ago, people discovered that neutrinos go faster than the speed of light.
Hi, people.
Right? I mean, that appears in the news everywhere, right?
2000
There is
and
an experiment
2007.
showing that neutrinos are going faster than the speed of light. It's a fact. I mean, we're saying it's a fact. They appear
It's true, yes.
So of course, the reaction of most of the people is it's true. I mean, it's not possible, right? That's the reaction. But it could have been true. I mean, we do not know. It could have been true. I mean, how do you know it's false? Of course, someone realized that there was a piece of the instrument that was disconnected somewhere. But suppose you do not know, and you cannot discover. What can you do? That is a question. What can you do to falsify that statement?
Correct.
Okay. So what certification is doing is saying, I am agnostic about theory. I only believe in outcomes, experimental outcomes.
Correct.
However, I need to logically consider all those outcomes in a particular way that I will cook up based on minimal assumptions. Okay, but using those minimal assumptions as minimal as possible, some witness that will decide for the outcome of that question. Okay, that is a very powerful thing. I mean, those arguments are not telling you, yeah, the speed of light should be, I don't know, 299. But no, it's not going to tell you that, but it's going to decide whether it makes sense or not what you're saying. So, in that sense, it's very powerful. It's not used heavily in experimental physics.
It
but
should be.
used.
It should be.
It should be used because it's a down-to-earth logical check of what you are doing. Just based on the outcomes of the experimental outcomes. And now going back to that, because I'm asking this question, do you know references or good references of people that are starting to use this idea to measure physical processes? I mean, you mentioned quantum gravity. I mean, it is, maybe it's, it's a kind of difficult thing, but there could be other things. For example, I mean, with Manic Neal, we did that for Majorana Fermi, okay, to prove existence or non-existence of Microsoft Majorana Fermi. But that was a tour de force.
What did you conclude?
Oh, no, we conclude. Oh, no. Let me tell you this. From the theoretical standpoint, I have my own theory, but this is, my own theory means it's based on my beliefs. Okay? My own theory of why it's those Majorana fermions they are trying to build could not exist. Okay. This is my belief. Someone can say, I don't share the same Bible. Okay, I have a different one, which is okay.
Yes, of course.
But then you have, what these protocols are telling you is that let's leave all the Bibles outside. Let's talk about minimal assumptions about some measurement without putting anything there. The minimal thing that there are, for example, 2 objects, 3 objects, 4 objects, whatever. And let's write some witness that will decide for your statement. Of course, if I put theory in the thing, some theories may coincide or not, but this is a different thing. Now, someone are claiming something. I mean, Majorana fermions are fermions, and they have the property of breathing in a particular way. So that is the reason why they are saying they have Majorana fermions. Otherwise, they cannot build this topological quantum computer, right? So this is, I mean, that's a claim. I mean, that is a claim. So this is a very powerful way of reasoning. Okay, so I mean, I don't know, how to extend this kind of reasoning to many other measurements. But I think that physics, theoretical physics, should start working more on this kind of.
I agree.
Because if you are working at the frontiers, it would be nice that there are this kind of logical tests that rely on any preconception, but on minimal assumptions that we can discuss. I'm assuming this, I'm assuming this, I'm assuming that. From that, I conclude this. Give me your data. I will tell you where your data and what we are saying is right. That's it.
What's logical difference on our assumption at the beginning?
No, because we make many assumptions. The idea of certification is minimal. Is this idea of device independence extraordinary? It's minimal. You want to relax almost everything. If I start telling you, okay, what I am measuring is gamma. Gamma is this operator. This operator has these properties. I have this wire is theta wire, and theta wire has these 0 nodes that are Majorana. That's a lot of information. I mean, who told you that this wire of indium arsenide in a superconductor, in proximity to the superconductor is theta wire? Who's telling you that? I mean, this is a huge assumption. I mean, this is that. Right? So in that sense, yeah, sure, there are some assumptions because you have to start from some minimal thing. But this device independence idea, what they do is minimize that information. You don't need an component, you don't need anything. You minimize the minimum amount of knowledge. Very powerful. Then someone can come and say, I can even, you have 3 assumptions, I can even do it with 2. It's better. And so on and so forth. So, I mean, I think that do you have any reference that tries to do, I mean, someone that, you know, I know the book of Valerio Scarani, that is pretty good, but it's mostly focused on quantum communication.
On physical theory, sort of testing of the, well, okay, there's work that is sufficiently related on, but not really fully related, on self-testing of quantum states that people do for generation of randomness.
Yeah.
There I do have some authors in mind. So people care about being able to prove that what they generated in their computer is that state, and they give some tests, but they're not device independent. They typically this literature is extremely device dependent and theory dependent. But to me, that would be, it's almost the same as saying that, yeah, you made it. You have a machine that behaves the way you say, but actually they say we have this noise and we don't want to rely too much on presuming that the computation went correctly. So we make some assumptions on the fact that it's quantum, some assumption on the fact that it was like this, but not too much. And then the rest is the self-testing. So that I know about. In terms of just using this for physics, so to test the reality of things in physics, so to ask what is a thing based on what we observe about a thing, I do not know of literature that does it in practice. I would be very much interested in doing some literature review on that. I think I shall task Nicola, who is now just apparently stacking arrays in Python. And so I will give him a new occupation for the weekend, which is to go and search for stuff like that. And if we find anything interesting, I shall send it your way. And we'll also want to look at it.
I know that the work we did with manual, because, you know, one of the things is that you basically want to self-test observable, not states.
Of course.
You can do well, but you like observable. That's what we want. But yeah, there are many questions. For example, how do I know? Look, I mean, one could do some sort of self-testing. We believe in LIGO, right?
We believe in?
We believe in LIGO.
LIGO, yeah, we believe in LIGO.
Can someone do something to certify, you know, some of these measurements independently of what they are measuring? Which I believe. It's not that I don't believe, sorry. But I'm saying this is the kind of thing that I'm saying that we should invest more time in this kind of thing if we want to.
I think we should do quite a lot of work in this. It is my next big stream of work will be trying to come up with frameworks for theories of physics, where we don't even assume that. I mentioned at some point today, when I say that a qubit comes out of this laboratory and that a qubit comes into that laboratory, what does it even mean? I mean, in space, how do I know that a qubit came in? Maybe I can send it in a container, but more often than not, there's some field that is traveling and there's a laser that carries it. There's some radio waves that carry it, something like that. And then you don't really know what you're receiving. You know that you're receiving something. And still, the reality is that if you have an interferometer and you look at the box in your interferometer when the photon doesn't pass into it, it's not that particles didn't pass it. It's not that there's no event. The vacuum did very much pass into it. And it is a property of certain measurement pieces that when the vacuum passes into them, they do nothing. There are other measurement pieces that when the vacuum passes into them, do stuff. For example, they continue randomly emitting pulses, and regardless of what the vacuum does. Of course, we have limitations on what can and cannot be done, but the idea is really you don't have to know the type of things coming in and types of things going out. All you really know is that there are some things you can do, and you can put some, maybe you can put some causal constraints about them, and that's it. You don't know how they're connected. You don't know what comes in. You don't know what comes out. And the reality is you don't care. All you care about is what you observe. And so you can ask, you can say, I presume that's what I draw there. You can say, I presume that I have some state, and I don't know what state it is. I don't even know if it's a quantum state for all that matters. I know that I can do some operations locally to this state. I presume I know I can do 3 operations, and I have some wires that come from somewhere. So maybe there's a state there, or whatever it means. These boxes are getting a bit of field into them, and they spit out a blinking light. When I press a button, there's a blinking light. And I want to say what I observed is proof that my wires add a GHZ state on them. Because, for example, I want to take I have the manufacturer that told me, man, you will get the best GHZ states in the world, super good fidelity, produced with like 95%. And here's your measurements that you can make. And I want to just check that that's true. I don't want to look into the wires. I don't want to look into a box because maybe I don't understand, or maybe I'm lazy. I don't know. But I want to test that this is the case. And so I want a witness that this thing is the GHZ state. And one way to do it is to say, I'm going to do operations that you tell me, the manufacturer, tell me that this is the GHZ state. And you tell me that the operations that I'm doing are measuring in the X and in the Y basis. And that's it. You guarantee me that those pieces of machinery do that the state that comes to GHZ state. And then I ask, what can I test? What are the witnesses that this is the GHZ state? And obviously I can gather tomographic evidence if I can repeat the same state again and again. But if every time I get a new state and I have to make sure that all of them are GHZ states, then I have to have a way of detecting whether I'm being cheated. Because sometimes that GHZ state is everything that stands between me and the nuclear launch codes being decrypted. And so, I mean, I don't know why anybody would use quantum cryptography for that, but apparently it's cool. So we ask, what is the GHZ state? How do I tell that I have a GHZ state? So I say, okay, I have this effectively the space of all possible tables that I can observe. I can pick some 0, 1, 1, 1, 0, 1, 1, 1, 0, and I have a bunch of outcomes that I can get 0, 0, 1, dot, 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 1, 1, 1, and I have some probabilities here. And each of these probability tables that I can observe is a point. Is a point in some big polytope. Not very big, but still big enough that you can't really visualize it, even for 3 parties. Even for 2 parties, it's too big to visualize. Well, hopefully it's not there actually, because that would be really bad. So let's say it's a point somewhere. And now I want to ask, okay, ideally I know the GHZ state should be under this testing protocol, the GHZ state should be on that face. It's nice. It's one of the great things of the GHZ states. The GHZ states are on kind of the boundary of this polytope. There is a direction beyond which you can't go. They're not in the middle. And so what I can say, and they're not at the corners. The corners are weird non-quantum things. But the GHZ states are in the middle. And what I can say is, is there a simple way of asking the question, how far am I from that face? Geometrically, just can I use the faces? Can I use my knowledge of the geometry of this polytope to determine tests that I can quickly do on the probability distributions that I get? And remember, each time I run, I am going to have to select one of them. So I do this many times, but each time I only get one witness. I don't get to measure the same state twice. It's the idea that you are making multiple measurements on the same state is predicated on the assumption that the measurements are the same across all rounds and that the state is the same across all rounds. And those are very big assumptions when someone is trying to cheat you and is giving you the measurement apparatus and the state. I mean, at that point, you're kind of you might think you're in the hands of the attacker, but you're not. And that's the beauty of it. And so you can say, I want a test that tells me how far I am from face over here. So I want to know whether I am kind of the GHZ state or I'm completely off base and I'm being lied to by my GHZ state provider. I should switch GHZ state provider. And so I ask, what is that face? What does the face of this polytope look like? Is there a nice way of testing these things? And it turns out that there is. And that the face of the polytope corresponds to one of these tables with 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0. I need them because otherwise I don't know which one I'm doing. 0, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 0. Okay. And then I say, okay, so I take the 1, 1, 1, 1, and then zeros in the other ones. And then I invert them. So like that. And then I use that as a mask. So I sum the probability every time I have, I get a probability, I get an outcome from my empirical model, from my tests. I run this protocol. I select randomly inputs for this protocol. I restrict myself to the case where I discard all the cases where there's like 001 or 100. Those I don't care about. And then I just look at the other cases and I say, every time that I get an output for a row that is not a 1, I mark it as an error. Every time I get an output for the row that is a 1, that's compatible with the observation. So it's not it doesn't become a what is the probability? Is it close enough? It's a yes/no question. Is my output compatible with the support of the empirical model? Is the output not compatible with the support of the empirical model? Then I do 1,000 of these tests. It could be that all of the states were different. It could be that the measurements changed every time because the person tried to cheat me by sort of, they have some sequence that optimizes the probability that it will look like a GHZ state, but it isn't really. It doesn't matter. If my error is below a certain threshold, I just have to count how many times I violate the constraints put by that table. I just count the number of errors. If they are below 0.1%, I have the probability that the person cheated is below 0.5%. There's like a small coefficient that you multiply by the error that gives you the fidelity for the state and the measurements simultaneously. And it's a yes/no test. And it only comes from the geometry of the polytope, because it turns out that the faces of this polytope are exactly the models which only have 1s and 0s. And that's it. That identifies a face. That's the support of a face. So a face is determined by these yes/no questions that you can use for self-test of any of these states. So if you know that the state should lie on a face and you want to test whether the state lies on that face, then all you have to do is like run these tests and count the number of times that you fell out of the support, fall out of the support, error, fall into the support, correct. So if you have 0, 0, 0, if you pick 0, 0, 0 as input and you got 0, 1, 1, then it's 0, 0, 0 as input and 0, 1, 1, it's 1. So that's a yes. And if instead you selected 1, 0, 1 and you got 0, 1, 1, then you go here, 1, 0, 1. And you select it again, you got again 0. Actually, let's pick a different one. Let's get 1, 1, 0. 1, 1, 0. And you get 1, 1, 0. You go check the thing at that row and column is at 0. So that's a no. And then you count the errors. Count the error fraction. And that is an estimate of the fidelity. And it's a completely theory independent device in the test that has nothing to do with anything else. And so you can use this kind of tests to determine whether you get the right state. And if you can put some theory dependent assumption in there.
Now I'm thinking, with a best state, you can do a similar thing.
Mm-hmm.
They felt truthful, the one that sold that machine was about that thing. You know, this is an example. Sorry? Which machine? We have one in the Mike's notes lab. That thing, there is a machine. Well, there is a machine. There is some apparatus that is producing supposedly some better state. So you can do this kind of test that we say, and then you can say, well, I mean, we paid $40,000 for something
That is probably not the best state. Yes.
and we were exceeded. For example, you see this kind of thing.
Mm.
I mean, which that, you know, it's just based on some logical minimal assumptions, and then we went.
And if you want to presume that you have quantum theory, say, because you like to live dangerously, then you can also say actually the subset of this polytope that is realizable in quantum theory is smaller, and so perhaps the phase itself would have many different explanations causally, but when it only touches quantum theory in one point, and then you know that you don't just have a state that is compatible with the GHD state, you know that you have for sure the GHD state because it's the only quantum realizable point. You know that the technique is quantum, so the only quantum realizable point is that point. And there you're certain. You don't even like have to presume. But maybe the aliens have weird states and they sold them to you, in which case,
So possibly the reason why this comes to trouble from other places, if there you have relativity gives you a lot.
Yeah.
That, you know, usually taken as one assumption. Special relativity holds and light, and then you can guarantee that it's going to be separate. So now, if you take that away, you probably get some no-go results based on simulatability. So, for example, when I given like the outputs of quantum computation, determine whether this was done using Majorana breeding or done using superconducting qubits in surface code, or done using trapped ions with some other fault tolerance scheme. Certainly for many of the outputs we get from these, the answer would probably be no. These can all simulate each other reasonably well. And so you can't really tell what's in the box. Now, I think the complexity theorists have nonetheless been attempting to recreate some of these ideas in their domains and say, well, okay, maybe you can't tell between these polynomially equivalent computation models, but if we believe, for example, that some problems are too hard for classical computers, we could tell that there's at least something beyond like finite dimensional or finite volume classical hardware. And that's, of course, led to a lot of press and a lot of controversy in its own. So they keep going back and forth over what's actually hard. And I mean, even like in the last few weeks, there's been like, there's that IBM paper saying, oh, we did this classically hard thing. And now two papers have come out saying they simulated it on a classical device. And so they're sort of creating these, creating over which assumptions really are reasonable, because they don't actually know what's hard classical in all of these cases. Like maybe if you have some much better density with them, a lot of these things become really easy. And again, I think that's actually going back to the fact that they're trying to do this without using any relativity.
Oh, yes.
And that makes it way, way harder. And so probably part of the challenge of doing this is figuring out like what is a very good assumption that can substitute for relativity when you can't rely on relativity to solve these sort of rules.
So you can, if you are willing to accept that it makes sense for measurements to be, for operations to be simultaneously definable. As in, if you are willing to identify the same operation done at 2 different times as the same operation, whatever that means, because it's not obvious to me that doing a C naught here and then a C naught here, or doing it this way is the same C naught. I don't. I am not sure, but if you assume some kind of time translation invariance on these operations that I apply, and you believe that when they send the pulse just at a different time, it is the same operation in the machine, which is a non-trivial assumption to make, and I am not sure that I would want to make it. If you presume that, then you can use contextuality, even in the absence of relativity. So you can say these measurements are commuting, not because I know what they are, but because I observe them to be. Because I observe that if I do, diagrams help in this case. So say that I do operation A, I have 3 quantum systems, okay? And I do operation 3 qubits, Q0, Q1, and Q2. And I do A and B. So I instruct my machine to perform this program and say that I get some, then I measure this. And I measure this. And then I do the same thing, but I instead do B first and A after. And presume that they have some parameter, theta 1, theta 2, theta 1, so that I can effectively have control over them. Because in quantum circuits, the control operations are just parametric gates. And what I observe is that if I don't look at the qubit at the end, the results are the same. So I get the same exact outcomes. So as maps, these 2 diagrams are identical. However, physically, who says that the A on the left is the same as the A on the right? Logically, you're telling me it's the same operation that you just did at 2 different times. But physically, how do I know? I mean, how do I know that your machine is even doing the same operation? How do I know that it's even possible to do the same operation at different times? Maybe they don't commute. I mean, maybe your machine destroys the qubits in the process of doing B, and therefore A cannot actually be done afterwards, and you're just getting noise. So it's an assumption that these 2 operations commute, and that when you say I do a gates in this order or gates in this order, I get the same result. Those are truly the same gates. It's effectively a time translation assumption on the system. But if you can presume this, then you can use this to say that A theta 1 and B theta 2 are simultaneously thank you, performed, and you can use contextuality to get something like the things that non-locality gives, and those don't require any separation, but they require this assumption of commutation. And the reason non-locality is a special example is because in non-locality you're performing your operations separated, so there's sort of a tensor network separation between them, and because they're separate, it doesn't matter which one you do first, there's no signaling between them. And so this is the special case of non-locality.
Yeah, but without no signal. All you see is the input. You also don't have the you know, it could be that what you do not, but it could also be that a classical simulation of quantum computer with a simulating quantum. Maybe what you're saying is that has to be honestly, quantum.
So if you can't, here's the only question that matters in this setup. No non-locality, so there's no physics that binds us. So the only question that matters is, are we willing to assume something about the reorderability of operations that we perform? Are we willing to presume that when we say the program does A at this step and B at this step, or we say the program does B at this step and A at this step, that A and B are the same? If we're willing to presume that, we can use contextuality to some extent. And that binds any realization of those boxes. They can be simulators, but if they can be reordered like that, that is a constraint that they have to obey. And contextuality allows you to do some stuff. If you don't believe that because you're true, like me, a truly like device independent absolutist, and you think, I don't know what's in the box, how do I mean, it could be anything. It could be someone with like an abacus that does the calculation very fast. Then there is nothing you can do. Then there is a theorem that states that without non-locality, there is always a classical explanation. There's many theorems that state that. The beauty is that even in the presence of indefinite causal order, so even if you presume that the parties can control the ordering of each other's actions because they have magical powers and they can invert pieces of space-time, there's still a classical explanation. So that, I mean, there's no hope there. If you can't look into the machine and you can't use physics to constrain you, or you can't use assumptions to constrain the behavior of the operations, there's nothing to do. I would say that this is not, that asking for that to be true is not a device-independent approach. That I would be in the camp of there's nothing you can say about it. Yeah, well, could be a gnome with an abacus for all I know. Maybe they're very fast at computing quantum things. Maybe someone discovered an algorithm, right? That does this very fast. They just didn't tell us. Someone has a proof that P is equal to NP, or that P is equal to P space, and they just kept it to themselves. They win at chess. They routinely get some money from our bank accounts without us knowing. I mean, that sort of things that people do. I wouldn't have. No, I wouldn't. I don't know. I mean, come on. It's like mathematical glory. Money, mathematical glory, money, mathematical glory. But yeah, it's interesting to figure out ways of doing this sort of self-testing with the minimum amount of what is reasonable. Like with the IBM machine, I do believe that their machines are quantum. They don't have to sell me to the fact that their technology is quantum. What I don't believe is that they can do anything useful today. And I'm proven right by the fact that tensor networks can do it. Same for Google, by the way. I don't believe their machine can do anything useful today, but it's still fun to use. I don't believe that the D-Wave machines do anything useful today. And yes, they are these humongous statistical systems that you can tune and play with from a website. That's beautiful to me. I mean, I love the idea that I can just make these Ising problems, send them and get statistics and try to like tweak the way that they change their Hamiltonian in time. That it's fun and experimentally very interesting because you have this nice, effectively condensed matter systems that you can control very accurately. It's just they are quantum because I can read the patents and I am convinced the thing is quantum, and it doesn't do anything useful from the point of view of quantum annealing. Say it can't do the quantum annealing algorithm because its coherence time is like yay small. So I don't know. I wouldn't trust that. I would trust that I do believe that they have a quantum computer. That doesn't change the fact that I don't necessarily think it's useful. Maybe that's the ultimate test. I like quantum, just as a brief final remark. I like quantum supremacy as an idea. The word could have been chosen better, but the idea originally was good. You want to have a test, a black box test. You don't trust anything. They have to show you a solution to a problem which you wouldn't believe a classical computer could solve. Now, whether you believe that P is different from P or not is a slightly different problem. But if someone breaks RSA in front of your eyes within a few minutes, they broke RSA or they have a quantum computer. I mean, if they're quantum computer manufacturers, I believe the second, not the first. I just believe that they were just very good. So in that sense, that test was okay as an idea, except we lost it along the way. And now I don't know what the word even means anymore. Yeah.
Yeah, I mean, is there any work that sort of study the limitation of this sort of approach, right? For example, I'm thinking, okay, let's go back to like 1960. Nobody knows about SU3 being a QSEc.
Right, all they see is they have this machine, collide a bunch of things together, and they assume that, well, anything come from a strong interaction. And you try to figure out what proof it is, right? And they discover like thousands of particles, right? From all these like scattering experiments, is there a way to certify that this must be acid-free and not gain? Like, so is there a study on the limitation between what you observe and what you can constrain?
This is a very nice question. I have, to some extent,
You have to find out,
a witness.
you have to, I mean, for example, what physicists, they were seeing some particular ordering, distinct way.
Right, exactly.
They were seeing a particular ordering of the energy levels. Okay, and from there, they speculate. They say that should be asymmetric. Okay, and they start talking about thought or something. But suppose that you don't have, in that case, I would say, well, what is that they are measuring? It was the energy, whatever. But now you can say, this is the reason why I'm asking the question, if there is any good review or whatever, but now you can say, okay, what kind of test I can perform where I'm using the minimum amount of information to certify that from those assumptions, this should be SU. SU3 is the right group. Yeah, and it's not obvious how to do that kind of thing. It's not obvious. That's, I'm asking the question because I think that we need to start thinking along this way, but I'm not sure that you can do that for anything. For everything, sir.
Also, he's asking whether, how do you know that it's unique?
Right, exactly.
Yeah.
Exactly.
So I think that's really the big problem with quantum gravity, right? You don't have any experiment at all.
None.
Now that
Zero.
everyone's guessing something, and let's suppose that we will never be able to perform anything that is even meaningful to come up with some theory. So you will never know what you can do, right? Or other criteria. Some people like me will be always method.
Yeah. I mean, how do you have to find a space of, okay, in the case of SU3, the situation at the time was that they were really looking at which group it was. They already knew something, right? They knew that it was a representation. They knew that they just didn't know what it would fit.
Well, there is always a bootstrap people, like,
They're asking.
yeah, exactly.
So you have some structure to your problem already. It's just that your state of possible answers is
The gauge group.
big.
Yeah.
Like the possible choices of gauge groups. With, by the way, what is the structure of the possible choices of gauge groups? What makes them? Are they sort of combinatorially separate? So like, are they discrete, or is there a continuum of deformations of objects between them? That's an important question to ask.
Exactly, yeah.
Because if you have, the thing is, typically when you have a continuum space, you can do something like local optimization, some kind of ascent or descent, maybe, and that makes your life a bit easier. If your space of possible states is combinatorial, so it's dots, then problems like these are typically really hard, because there's no, I go a little bit in the right direction and I deform until I get the right point. But still, you can think of from the kind of observations that come from these groups, the various group choices, you could think of what is the space of possible outcomes I get. And if you can pick a face or
They were
slice.
I didn't follow it, but these people were talking about EA.
Yes.
We're going beyond this. So this is probably something different. Okay? What kind of self-testing generate that is going to falsify, or going to certify EA versus SU, or things like that? I mean, things like that. But it starts to be interesting, because now you don't know You propose a measurement, and then, the physics will tell you.
Yeah.
Whether the question you're asking is consistent with, the answer from the experiment is consistent with a particular picture or with another picture.
Right, I mean, it's like, that's what pen.
For example,
People have been looking for photon decay for many decades, and they find it. When is the right time to quit?
But
Sure.
I think that is a problem, right? Because they currently, the way that they think about the problem is that they rely on this one measurement, one single measurement of photon decay.
Yeah,
To conclude.
that's
the-
true.
But
they don't have choice. There's no optionality. Therefore, there cannot actually be any
the photon decay.
problem. Okay.
But they claim that the non-observable photon decay implies basically, that it's not SO10. But yeah, what I'm trying to point out is that like in all this scattering experiment or particle collider, they make this statement and they claim it to, if you observe this process, then you already have that. But can we combine different measurements together?
I think so. I just very hard.
No, they did. The good question, this is a question I always get asked to your guys, about when they come to give a colloquium, they are talking about double beta decay and, that is these neutrinos are Majorana. I always have the same question. How do you know they are Majorana?
Correct.
Well, the theory tells that it's Majorana. But
Well, you don't know. You have no way of verifying that. Yeah, that's true.
why do you believe it like that? I don't understand. So there should be a way of building some self-testing protocol that will say, we take the measurements, do this, and if this happens and you get this witness, whatever, this is Majorana, or it's consistent with Majorana, let's say, something like that.
A lot of science is based on sort of Bayesian. You have prior, and you do some experiment based on your prior. Then if you got right, then you update it. So basically, that's the sort of traditional way of doing science, right? And that's the way that.
Right, that's the way we do science, but the thing is that there are the way we analyze data indeed is there is this preconception that we should see something.
Yeah.
And what these certification protocols are trying to eliminate as much as possible your preconception.
Right, that's what
Is the hallucination implicit in the looking at data while searching for
Right, so
something?
this
You're going to
is-
hallucinate here's my proof. It's like, no, well,
I mean, good example is the recent photograph of the Dorsey of the blood, right? I mean, because really they use the sort of
Adrian,
machine learning to the
Shall I
size data.
pause it's recording, but most of it is not. Sorry, just most of it is not. Yeah, shall I just? No, it's just that you're gonna have a very long video where you can't. I don't think you can really hear what any of them are saying. So
There's no video right now.
no, I mean a very long stream. Yeah, recording where you're gonna
You
not.
want to disconnect?
Yeah, if you think, I think we can continue the conversation without it being on.
If you disconnect, this will show you at least. Whatever you're talking, will show you.
Sure.
But you have to disconnect.
Yeah.
So yesterday, whatever we talked, we recorded, we did it. So if you disconnect, there will be just the picture. And that.
That it's one event, right? So basically say, people have been studying years for inflationary model fits or whatever that we're seeing, but at the end of the day, you've got to ask me, why? How do you know that's the right?
Yeah, I think the black hole, the Event Horizon Telescope process was actually particularly interesting in the sense because they really didn't have an image, right?
Right.
What they presented was what they called a fiducial image, which means they sampled loads of images compatible with the data and they mixed them with a fairly complicated problem, not really complicated. They just sampled a lot of them, weighed them and mixed them, and they told you this is the weight result. So that's as Bayesian as it gets, right? But is that, in a sense, really, is that a picture? Yes. Is that a picture? No. That's an interesting question. Is the picture not like things? And I think that I would consider that it's not what it's for use. It's not a big dance in the process. Then you have to talk like but Samsung is a good I think if it's something new and it has very nice visible crater, and I am sure are not there in the picture. It's just that Samsung has a map of the moon and it puts it onto my picture and it makes it look nice. I don't know, is that a picture visible? I wouldn't say.
So I think there's a broad issue of inductive bias, and this is studied from machine learning, because there are these ideas of no free lunches that saying that there's no way to universally make your model better at capturing all functions. No matter what you do, you're going to introduce some bias. And so you're just hoping to introduce a bias towards the thing that's useful or correct or that you believe, and away from things that are useless or wacky or whatever. And in physics, it seems like often we do have these situations where at least people believe that there are very few models that have any real prior probability of being true. And so one can create an experiment that distinguishes between them. But of course, one could challenge this, and people do, and that's kind of what device independence is looking for, is that, like, okay, how much is this really using inductive bias to make a conclusion versus how much of it is actually coming from the experiment? I've had some contact with fields where the picture is very, very different. So like in trying to infer a model from ecological time series data. This is really hard in many cases because often you're going to have some complex system with like potentially hundreds of moving parts. You can try to like put a model structure on it, like a Locke-Terra model or something, but that is a problem that you might be kind of unproductively biasing it. Maybe those assumptions are not right. You can try to do this in like a fully data-driven way, but I think it's been well observed now that there's papers on like the cost of complexity. And so these will actually, because of bias variance trade-offs and noise and such, find simple models that probably are not really capturing today. They're just sort of maybe local optima in the trade-off between the model being noise robust and still having enough, still having a little bit of information about the system. And so these are things I would describe as having a very not peaky landscape of prior probability and models. Like there's a huge space of models. A lot of them look very similar to each other. And so it's very hard to make this inference or say, okay, this really strongly points to this conclusion and not that conclusion, and not something in the middle. And it's really the in the middle that I think gets you into trouble, where it's like, okay, we could explain these results really well with this model, but pretty well with this other model, and decently well with 1,000 other models. And I think with device independence, I mean, cryptographers, and I think this was also one of the influences going into why device independence seems to come up so much communication, cartographers also think about this problem a lot. And from sort of a different perspective, which is, well, let's try to be really, really sure that it isn't like some adversary. And so in some ways they're on the very extreme end of like, let's try to assume that as little as possible, because basically they're paid to be paranoid. And so I think that you could actually sort of widen this question to that of like, it's related to some of these other questions of how do you introduce priors when you're trying to evaluate models? And in some cases, it's sort of maybe we believe that it's kind of clear. We have good assumptions we trust well, again, relativity, or maybe some of these contextuality things, people interchange stuff. And in other cases, it's sort of like, well, actually, we don't really know that much. And there's lots of open problems, I think, in terms of whether there actually is a good inductive bias in many of these cases that we haven't discovered, or if, in fact, you shouldn't really trust anything.
All bias have just experimental risks.
I don't know. I mean, I would say that theory could be a fun. Like with this thing with the Whitney thing, like SU3 and those E8 stuff. Sort of narrowing it down to the space where you say, well, it is a group representation. It is a gauge group. I mean, a lot of theory went into it.
Yeah, no, it is here. When you're doing experiments, if you have some theory.
No, I'm saying like even from the algebra, like if you say that 1 + 1 = 2, that's not like a theory, that's an experimental fact that you could have one thing, you could do another thing and count from 0 again, you get 2.
Yeah.
That's an experimental fact. Right?
What do you use there?
Yeah, it is. It is with one condition, which is that you're identifying what
Exactly.
1 is and what 2 is. So it is an experimental fact, but together with an equivalence class of things that you deem to be the same.
So those things are theoretical, but the process is
No,
experimental.
they're practical. It's all experimental. I agree. I'm saying it's not just that the experiment that says that when you take one thing and you put it next to one thing, you get 2 things. Is the repetition of the same thing again and again and again, but subject to what you define to be 1 and what you define to be 2. So it's just that you have deemed that this is 1 in a sense, and this is 1, and when you put them together, you get something that you recognize or deem to be 2. But you could have, as what someone else with a different conceptual system could say, this is many, this is much, and this is much. And it's a different kind of much. And maybe I care that maybe if I put them like this, or if I put them like this, they're different to me, maybe they're not. Like these could be spins. They could not be 1. Maybe someone doesn't have a concept of numbers, but has a well-defined concept of orientation of things and says, I mean, I don't care that they're 2, because to me, this and this and this and this are 4 different things. And then they're longer too. So there is a certain, you have to collapse
That
things.
those things are 4 different things. That is an experimental fact, right? That is
No, yeah, I agree. I agree. It's just that we tend to sort of forget them.
I mean, I think the theory comes in when you're trying to generalize or to say that any experiments done at different times or places have anything to do with them.
Yeah, it's an equivalence.
Like, I could say I don't believe the Bell test because I think that this past year the speed of light just completely changed. But as a theorist, I don't think that's very likely.
I mean, from an experimental perspective, that is also not really likely because the speed of light is a constant. That's like maybe the 99.9%. We are sure because of like experiments on that.
But there's still some induction. So something keep doing this experiment and keep getting this result. Therefore, we believe that well, it's constant.
I mean, up to some probability, of course. Like we are not 100% sure that it's a constant.
Okay. I wouldn't put probability into it quite yet, because I don't think you need it. Because I think this sheer act, it's not even about probability, it's the act of you identifying, without thinking of probabilities, you identify the things that you call a Bell test. And you say, these are Bell states, these are measurements, these are things that I recognize to have the shape of a bell test, and I glue them together, and I say, here is my probability distribution. It comes from the gluing, but really they are individual events in time that you have sort of taken to be the same thing, and it's that act of identifying them that gives you probabilities, that gives you confidence in the fact that the speed of light is constant, that gives you constant confidence in the law of physics.
Even without Bell state, like we can still find out if speed of light is constant or not after some probability. Like even without Bell state, you don't have to go to Bell state probability. Like if we want to find out if the speed of light is constant or not, we can say that this is constant, but we are doing like 99.9% sure.
That's the part that I don't even think. That's the Bayesian part, and I'm a frequentist, and to me that doesn't exist. I don't know what it means to be 99.999% certain of a fact that I've never seen falsified. If I've never seen it falsified, there is no percentage of, there is no definition of what it means to probabilistically be sure. I'm sure of it because I've only seen it done that way. In order to imagine that it has a probability, I have to imagine a future in which I've done this experiment infinitely many times. And perhaps sometime I see a mistake. And there, the probability comes into play. I can say I'm 99.9% sure because I've done this experiment 100 times, and one time I got a result that was dodgy. And that makes me 99.9% sure, maybe. But if I see the same thing again and again, and the event never happened, then presuming that it has a probability is a lie.
That when you do the experiment, let's say you want to find a value, you don't find that value all the time. Sometimes you get something you get a little bit different on the other side. So that's how you get the probability. So like out of like the experiment that I have done like 100 times, 99 times I have got like constant. One time I got it was not constant. It's not that I've never seen that it's not.
I guess
There are a few times that I saw that it's not.
You're right. How do you measure the speed of light?
I mean, I guess like you can measure it in different ways. It's like Fizo, it was like was zero. You can still use those.
But you are putting in an equivalence that states that all of those quantities that you measured at all of those different times, in all of those different places, with all of those different machineries, were the same speed of light. You don't know that. I don't know that. I'm saying that it's the act of making them together that makes you confident. So it is all experimental. There is no theory. The theory is just the act of giving things to equal. So you say the speed of light is this and this and this and this and this and this, and then you sort of abstract it into a compressed model that states that gives you rules for identifying new ways in which that is the speed of light. But you could also live in a universe where you say, I don't care that there is a quantity called the speed of light. I know I can do this experiment and this experiment and this experiment, and they all agree. They always give me, they're correlated. But someone could have a conceptual system where they don't say, therefore there must be something underneath that is common. So you could say that that's the speed of light, or you could say that's the speed of light 1, the speed of light 2, the speed of light 3, and maybe they're not the same thing. Maybe they are. But still, I'm saying it's even better than, you don't even need to say I'm certain with some probability. I'm saying if you can consistently reproduce the same thing, then that's it. That's what you're saying.
But I'm saying that you cannot consistently reproduce the same thing, just like because of like for various reasons, the values is a little bit different. That's where the how certain iron comes in. Like we cannot reproduce the same result every time. We need to do everything exactly the same.
But you do know consistently that you cannot signal. Actually, that's an interesting question. Do you know consistently that you cannot signal faster than light? Is there a way of doing that non-statistically? No, not really. Yes, there is. Yes.
I think they are talking about
Now
you're talking about uncertainty measure.
yeah, I think so.
I'm talking about
a different
certainty of the measurement, which is different.
But I think what I think we're saying is that if we do if we want to find the speed of light, and if we see that we have done this 1,000 times and we have always found out that the speed of light is constant, then you are saying from frequency perspective that speed of light is constant, then we are 100% sure about it.
No, I'm saying that that you can't assign a probability to the idea that something is not, that it is not constant, because there is no meaning to the probability.
But I'm saying from experimental perspective, if you do that 1,000 times, you are not going to see that all of those times speed of light was constant.
No.
Maybe 90 times.
So
so there are few times when it was not constant. I'm saying the probability comes from that idea that Like, because like there are like 10 times where I saw that it's not constant, so now I'm 99% sure that speed of light is constant.
I see what you mean. Yes, but you're not really sure it's constant though at that point.
Yeah, I mean, I'm 99% sure, but not more than, yeah.
How can you be if you
Sure,
should differ?
certain measure.
Yeah,
Okay, but you cannot, how can I say, you cannot guarantee. Okay, that is constant, but the fact that it's constant is coming from a theoretical constraint. Okay, so this is a theoretical constraint. What you are doing when you are doing experimentally, you have an uncertainty because you are doing a measurement, and you know. But what happens if for some reason the universe is expanding? And you know, the way the speed of light is changing in the 100 digit, right? Okay, and you will never see.
Say, I think it's not just about the model, to the framework.
Yeah.
You know, but you're saying that, oh, I'm gonna bounce the light between the two mirrors and say measure the speed of light. You actually need a conceptual framework that what defines the speed of light.
Yeah.
Exactly that computer setting. And that's what I think we define by the theory.
Yeah,
And
that's a theoretical construct. That's a framework.
right.
Also,
So when you're designing an experiment, you really have to have a I think that's what
yeah, no, absolutely. But I think that when you don't want to say probability, this is the uncertainty in your measure. That's what you're measuring.
but more than
If
anything.
you don't know what is the probability that is constant, how do you know?
Yeah,
Because I'm telling you.
and do you need to know?
Sorry?
Do you need to know?
No.
Physics,
Well, it depends. I mean,
No.
it depends. Well, it depends. For example, let's assume that you can measure now. I mean, you can measure now. I mean, you need to know. I mean, for example, LIGO needed to do all this kind of development, experimental to guarantee the existence of the gravitational wave. Now, is there some experiment that, for example, you need to know the speed of light up to, you know, how many digits, I don't know, 100 digits, let's say, in order to rule out some other thing. Let's assume.
Then yes, then you need to know that it is.
You would have to do that measurement to find these 100 digits to rule out something. But you cannot say that we know with some probability. That's uncertainty in your measure. But you do not know. This is the example I was telling you. Suppose that the universe is expanding, but in a way that the speed of light is changing, you know, 10 to the minus the age of the universe every 100 years. So how can you say that with probability, whatever, because the only thing you're measuring, the uncertainty of your measurement, that is happening. How do you know? I mean, 100 years from there. I mean, yeah, sure, you can go from one to the next one and refine the uncertainty.
I think we should leave this for next year.
Yeah, sorry.
This is the end of the week. I would like you to please join me in thanking the speaker.
Yes.
The speaker and thank you for coming over here.
And
And
almost be fun.
yeah.
We can continue, but we don't have dinner until like 6.
yeah, but we have to be there at 6 and we cannot teleport us.
Oh, it's in an hour. Is it at 6 or 6:45?
6:45.
So when do we have to be there?
Yeah, well, you really 6:45.
Okay, so.
So I need to be there a little bit earlier, so I'll go early. But I mean, it's
But where
okay.
is it far?
Well,
No, it's downtown. Okay, so we don't. really have to
downtown
go
is
anywhere
not,
right now.
it's downtown. I mean,
We can actually sit and.
That's important.
I want to pick up my car.
Yeah, so, we can continue the discussion over there. 'Cause
Yeah, well, I mean, we can move and continue somewhere there, but I'd like to continue that discussion because that's an important point.
Sure.
I'm not sorry, it's like, why anyone else?
I'm not really confident anymore.
No, it's not. I'm saying the statement that your statement, the speed of light is constant, is the
Oh, I see.
identification of all of these experiments. And it's the idea that it's not constant, obviously, because you measure it differently, but you're saying something slightly different. You're saying, in all, I deem that when I do these experiments, I'm measuring the correlated quantity. And furthermore, I deem that the more I measure it, the narrower my